Hey everyone, Mr. Armitage here, and in this video, I'm doing something a little different. In this video, I am offering a proof of the rational root theorem. So this is showing why it works. Okay, why can this happen? Okay, so the rational root theorem simply states that if we have a polynomial, so a sub n times x to the n, plus a sub n minus 1 times x to the n minus 1 plus ... plus a sub 1 times x plus a sub 0 equals 0 with integer coefficients. Okay, so all of those values of a are integers. Then each rational solution of this polynomial, so x equals p over q, right? Rational, ratio, a fraction, will be when p is an integer factor of a sub 0, which is our constant term, and q is an integer factor of a sub n, which is our leading coefficient. Constant term. Here, this is the leading coefficient. Okay, and by polynomial, right, obviously these are all variables and parameters, but simply all I'm saying is that we have some polynomial example like a 6x to the 4th plus 3x to the 3rd minus 2x squared plus 7x minus 10 equals 0. Okay, so in this case, our constant term would be negative 10, right? A sub 0. And our leading coefficient would be 6, a sub n. A sub n there, a sub 0 there. Now, all of our rational solutions, all of our solutions that can be represented as a fraction will be made of factors of these two numbers. Okay? So how does this work? Well, or why does this work, not how. There's another video that shows how it works in the previous, well, link up there for an example of how this works. But we want to see why it works. Okay, so let's go ahead and take a look. Okay, if we do have a solution, so if x equals p over q is a solution, well, what does that mean? That means then if we plug this in as a solution, it should equal 0. Okay? So you should know that a sub n raised to the power n plus a sub n minus 1, and I'll put these in here in a second. N minus 1 plus ... Okay, because I don't want to write it down each time and change the colors. Okay. There we go. A sub 1 times p over q plus a sub 0 equals 0. If it is a solution, this is a true statement. Okay, so not bad. Well, the nice thing about this is that if it's true, as long as we're consistent, anything we do to it will keep its truthfulness. So let's multiply by q. Okay. So we're just going to multiply, well, not just q. Okay. We're going to multiply this entire equation by q to the power of n. Okay, whatever n is, our degree. Well, our first result would give us a sub n times p to the power of n. Right, the q to the power of n's cancel out. Then we get plus a sub n minus 1 times p to the power of n minus 1. Now, n minus 1 is 1 less than n, so we have a q here as well. All right. Plus, here. We can do one more term just to see what it looks like. So a sub n minus 2 times p to the power of n minus 2. Now, n minus 2 is 2 less than n, so this would be q to the power of 2. Plus, on and on like that, until we get to the end. So we have a sub 1 times p to the first power times q to the power of n minus 1 plus a sub 0 times q to the power of n equals 0. Okay. See here, right? A sub 0 times q to the power of n would be a sub 0 times q to the power of n. Okay. So all we did was multiply by a common value to get rid of fractions. All right, pretty nice. Okay, well, why don't we subtract this term? Okay, so we'll subtract a sub 0 q sub n from both sides. Okay. So that would give us, well, we would get this here. Okay, I'm not going to rewrite it. Equals negative. Oops. Actually, I wanted to keep all the colors. There we go. Okay. Equals negative a sub 0 times q to the power of n. Now, why is that important? Well, now look at what every term on the left side has. Okay, we can, in a sense, factor by greatest common factor. Okay, we can factor out p. From just the left-hand side. Okay, so we have p times a sub n times p to the power of no longer n, but n minus 1, okay, because we had factored that out, plus a sub n minus 1 times p, no longer the n minus 1, but now n minus 2, because we took 1 out. Okay? And we still have this q here. Okay? So the exponent on the p's decrease by 1 each time. Okay, plus on and on until we get to our last term here. We have a sub 1. Now we factored out the p, so that's no longer there. And we simply have, oops, q to the power of n minus 1. Okay. And this still equals negative a sub 0 times q to the power of n. All right, well, what does this mean? Well, this means p times something equals what's on the right, which means that p can divide what's on the right side. But since, no, well, there is a special term here, but we know that p cannot divide q to the nth power because they are something called coprime. They don't share any factors. Therefore, if you multiply them together, or you keep multiplying it, one of the terms by itself, it'll never be a factor, right? 2 and 3 are coprime. So if we do 3 times 3, that's 9. Still not divisible by 2. 3 times 3 times 3, 27. Still not divisible by 2. So that means that p must be able to divide a sub 0. Here we go. Okay. Because p cannot divide q to the n, that means that p must divide or must be a factor of a sub 0. Okay, so that's all well and good. So we know that p is a factor of a sub 0. What does that mean for q, though? Okay, we haven't said anything about q. All we're saying is that p is a factor of a sub 0, our constant term, which we got above. Well, we need to take a few steps back. Okay? We need to look at here. Okay, so we're going to start from this side. So right before we subtract, right? So now, instead of subtracting our constant term, a sub 0, let's subtract the leading term, a sub n times p to the nth power from both sides. So that will give us this part here. Okay. Equals negative a sub n times p to the nth power. And now we essentially do the same thing that we did before. Okay, we factor out a q because we see that each of these terms here has a q in them, has a q in it. Right? So we can say q times a sub n minus 1 times p to the power of n minus 1. Now there's no more q there because we factored it out. So we have plus a sub n minus 2 times p to the n minus 2. And we factored out a q. So instead of q squared, we just have q to the first. Plus on and on. Here, a sub 1 times p, because p is still there, times q. Instead of n minus 1, we have 1 less than that, so n minus 2, plus a sub 0 times q raised to the power of n minus 1. That equals a negative a sub n times p to the nth power. There we go. Okay, now we use the same argument that we did before. Okay? We know that q cannot divide p to the n. But we know that q times something equals p to the power of n times something else. Well, q must divide that something else. Which is the a sub n, which means that q is a factor of a sub n. Q is a factor of a sub n. P is a factor of a sub 0, which was our original premise for the rational root theorem. Right? So that was a proof of it. It was very loose as far as true mathematical rigor goes, but it should give you an idea of like why it works and why do we have to deal with the factors of the constant term and the leading coefficient.